3D applications today are still largely controlled by 2D WIMP user interfaces. We are interested in developing fully 3D user interfaces that augment direct manipulation with 3D widgets, that is, encapsulations of geometry and behavior. In this video paper, we present a toolkit that enables designers to rapidly and visually prototype a variety of 3D widgets and to constrain certain basic relations, based on affine transformations, between them. Application objects and 3D widgets are created in the same environment, our unified graphics architecture, modeling, and animation system. Thus, there is no intrinsic distinction between them, making it natural for 3D widgets to participate in constraint relationships with application objects. All demonstrations in this video were recorded in real time. Our toolkit consists of a collection of primitive widgets. Each primitive is composed of a set of ports that correspond visually and functionally to one or more of the constraint values that parameterize the primitive. The first row of the toolkit contains the most basic primitives, which have only a single port. The second row shows composite primitives, which have multiple ports, some of which are just instantiations of the basic primitives. Bidirectional constraints are used to relate ports on different widgets to one another. The bottom row shows more abstract black box primitives. These primitives encapsulate arbitrarily complex relationships. Let's look at the first row of widget primitives. All the traditional objects in our modeler, primitive solids, CSG combinations, sweeps, and patches, can be used with the widget primitives as a final geometric representation for underlying widget constructions. We collectively refer to these modeler objects as geometries. The point primitive represents a single parameter, a three-space position. The ray primitive's single port represents two parameters, a position and an orientation. Looking at the middle row, the length widget has four ports, the two endpoints, the line through them, and a marker at the midpoint which represents the distance between the endpoints. This widget can be used to calculate linear distances or constrain translation to a line. Next, the angle widget computes the angular measure between two orientations. These orientations are commonly produced by rays linked to the handles of the angle widget. The next primitive, the oriented plane, represents both a 2D Cartesian plane and a 3D Cartesian space. The plane consists of a number of components, including a rectangle centered about an origin point, which is initially green, and the normal and up vectors, which are initially yellow. The rectangle represents the size of unit vectors in the x and y axes of the plane and can be resized interactively. The cube at the top of the up vector represents the 3D Cartesian space. The final two primitive widgets are the black boxes for specifying parameters of cameras and deformations. These black boxes, used later in this presentation, consist of an array of ports representing parameters to high-level functions. For example, the function in the deformation box on the right computes twists, tapers, and bends based on its input ports. We expect to expand this collection of black box widgets as needed. In order to create more complicated widgets from our primitives, we need a way to specify relationships between them. These pairwise relationships are often in the form of geometric constraints, but can also function as more abstract values, such as camera or deformation parameters. All relationships are persistent and maintained by our underlying software system. As a first example of specifying relationships between widgets, we create a simple composite widget that scales an arbitrary object along an axis. The first step is to define the axis of scaling. We do this by constraining a length widget to a ray. Constraints are bidirectional and involve a from and a to object. To specify this constraint, we first select with the mouse the object we wish to constrain, one endpoint of the length widget. The shape of the cursor indicates that we are selecting the from object. When the endpoint is selected, it highlights purple, and the cursor changes to indicate that we can now select the to object. Note that objects only highlight purple when being linked together with constraints. We then select the ray, and it too turns purple. Now the cursor indicates that the system is waiting for user confirmation. We click again with the mouse to confirm this constraint. Now the endpoint is linked to the ray, and it turns yellow to indicate that it has been partially constrained. We use colors to indicate the degree to which objects are constrained. The point is now constrained to lie on the ray. This process of establishing relationships is called linking. We similarly link the other endpoint of the length widget to the same ray. The exact semantics of a link depend on the objects involved and what constraints may already be in effect. Next, we use our modeler to pop up a simple geometry that we want to scale, a cone. We link the cone to the length widget. Notice that the semantics of this particular link relates only the scale parameter of the cone to the length primitive. This scales the cone along the axis of the length widget, thus skewing it. To scale the cone about its principal axis, we align it with the ray by linking it to the ray. Now the cone scales along its y-axis. The plane, length, and ray widgets can be used to constrain the degrees of freedom of other application objects or widgets. In this example, we will use these three primitives to create a handled widget that rotates about a single axis. First, we link the origin of the plane's widget to the body of the length widget. This constrains the plane's origin to lie on the length widget. We then link the plane normal to the length widget to make the plane perpendicular to the length widget. Next, we link a ray to the plane to constrain its rotation around the plane's normal. Finally, we link the ray to the plane's origin. We undraw the plane widget to unclutter the screen and manipulate the resulting widget. Notice that even though parts of the composite widget are not visible, their effects are still active. The constraints resulting from links propagate through connected components of the construction. In this example, the origin of the ray is constrained to translate along the length widget, just as the plane's origin was. In the following segments, we demonstrate a number of uses for this toolkit. We use it to construct application objects, 3D widgets, and a prototype interactive illustration. In this segment, we show how to use our toolkit to embed interactive controls into a 3D scene. This model of an amphibian aircraft, created in our 3D modeler, has a number of control surfaces, ailerons on the wing and canards near the front. Pin joints have been defined between parts of the aircraft. When the user rotates the red handle of a joint widget, the attached control surface rotates about a single axis. With this model, users may only manipulate a single joint at a time. Our task is to construct a user-controllable yoke that provides simultaneous control of multiple joints with a 3D interface that is both realistic and understandable. This is a good example of the utility of breaking down the distinction between application objects and widgets. Our widget toolkit is used to define the behavioral scaffolding of the yoke, which is an application object. We begin with a ray to control the rotation of the ailerons. In order to constrain the ray's rotation to one axis, we link it to the coordinate system of a plane widget. Another ray is used to define the axis along which the yoke will translate. We link both the plane's origin and the plane normal to the ray. This permits push and pull interactions. At this point, we have defined the general interaction of the yoke parts. Next, we must derive values from the position and orientation of the yoke to control the joints on the aircraft. First, a length widget is used to calculate the in-out position of the yoke. Similarly, an angle widget computes the angle between the user-manipulable ray and the up vector of the plane widget. For clarity, we also link the angle widget to the center of the plane widget and undraw the rectangle. This is now the abstract representation of the yoke with length and angle measurements. A previously modeled instrument panel defines a location and coordinate system for the yoke. The panel gives a more familiar metaphor for housing the airplane controls than the abstract intermediary objects alone. A previously modeled representation of an actual yoke is now attached to the abstract yoke assembly by linking its position and orientation to the assembly. Linking the body of a joint to a length widget or the output of an angle widget makes the joint's rotation dependent on the length or angle measured. We thus link the 4 joints to the appropriate parts of the yoke control. We undraw many of the underlying widget primitives and the joints, so that the user is presented only with the yoke handle as an interface. This simplifies the appearance and use of the widget. The user now controls the canard surfaces and ailerons by manipulating the yoke. The ailerons move in opposite directions because one of the joints was rotated 180 degrees during its initial placement.